At section 3.2, verifying trigonometric identities. So we'll need to probably do some factoring from our algebra days. So we're going to compare algebraic factoring to trig factoring. So here we have difference of perfect squares. You probably remember you have a conjugate pair, 1 plus 1 minus. You take the square root of each term, 2y and 7. 2y plus 7, 2y minus 7. The same holds true over here. For trig function, side squared theta is a perfect square. 1's a perfect square, and you're subtracting it. So this becomes sine theta plus 1 times sine theta minus 1, both in parentheses. They are binomials. If you have a trinomial leading off with a 1x squared, remember we read this backwards. What two numbers multiply to be 6 and subtract to be a negative 1? That'd be a negative 3 and a positive 2. And there's our two binomials, x plus 2x minus 3, and it doesn't matter which order the binomials come in, it's still correct. So over here you can think of this as 1x squared plus 3x minus 40 if you wanted to. What two numbers multiply to be 40 and subtract to be a 3? Now one of the key things here is 3 being odd. Think of an odd factor inside of 40, because the only way that you can add or subtract two numbers to get an odd number, one has to be even, one has to be odd. So don't go to 4 and 10 or 2 and 20. They're both even. We need 5 and 8. If you look at 5 and 8, that subtracts to be to 3. So we'll have an x plus 8 and an x minus 5. The plus 3 says, hey, bigger number, you carry the sign. So that carries over to here. It'd be sine of x plus 8, sine of x minus 5. Or if you will, theta. I prefer thetas when I write my trig functions. I'm not a fan of x's. I use x's when I'm dealing with algebra. So I apologize for that. I guess we should change that back into thetas. I mean, I did it again. Put them in x's, if you will. So I apologize for that habit. I'll probably do it again in the next one. Okay, E, here we have something other than 1 in front. So here we go. To factor this, I do factor by grouping. What I'm going to do is I'm going to use what we call ABC method. A is the 2, B is the 5, C is the minus 12. I am going to do the FOIL process backwards. You combine the two middle terms to get to 5x. We have to separate them. These two blanks right here, call that the two blanks in the ABC method of factoring. What two numbers multiply to be AC? And those same two numbers add up to be B. So 2 times negative 12, and B is 5. Again, don't multiply this together. It's not needed. 5 again is odd. You need an odd factor. All right, so I have to go to 12. There's a 3 as a factor in 12. So break it down to 4 and 3. 4, you get traded to the 2. 4 times 2 is 8. There's your 8 and 3. And again, because 5 was positive, 8 gets the positive. The smaller factor, 3, gets the negative. So the 8, positive 8, goes with the plus blank. That's going to be 8x. The negative 3 goes with the minus blank. Now, you may have wanted to know, how did I know one was a plus x, one was a minus x? You recall, when you factor, when this is a minus and the c is a minus, these two signs are always opposite of each other. When are these signs the same? Is when this is a plus. If my c was a plus, then the two signs will be exactly the same as the middle term. If this is a plus, then it's plus plus. If it's a minus, it's minus minus. Now that we have the O and the I term of the FOIL process, we cut it in half when we do factor by grouping. We're going to take out a 2x from the left and get an x plus 4. And you have to have an x plus 4 on the right because we made the blanks up here for the ABC rule to work, which means I have to have a negative 3 as my GCF. So now you've gone to 4 terms to 2 terms. This is technically one term. This is one term. Out of these two terms, x plus 4 is the same. That's one of my factors. The individual GCF of the left and the one on the right, they build the second factor, and now we are done factoring. Over here, again, if you want to treat it like 2x squared plus 3x plus 1, this is a shortcut. This may occur. 2 is prime. The only numbers for factors are 2 and 1x. Your constant 1 is 1 and 1. Your two signs are both plus, so they're going to be positive. Remember I said if this is a plus, then my two terms are a plus. There they are. So again, there's my sine thetas again. So replacing sine theta, or actually sine x. You can go ahead and put sine x or sine theta. Either one's fine by me. All right, perfect cubes. Oh, I apologize for that tickle. All right, perfect cubes. This never, ever, ever factors to 3 binomials. I guarantee you will get it wrong. This factors to a binomial and a trinomial, and while you fill out the blanks, fill in the signs. Clean up the signs with SOAP. It's an acronym that stands, S stands for the same sign you were given in the problem, O stands for the opposite sign in the problem, and AP always stands for always plus. Once you have the outline done, take the cube root of both terms, x and 3. Now here, you smile because you're almost done. What you literally do is think about drawing a circular arrow to the x itself. So x times x, x squared. X times 3 is 3x, and 3 times 3 is 9. And if you did draw those circles in there and this big arc, you'll see a smiley face. So the same thing can be done over here. We're just going to need bigger blanks because we have to put trig functions in it. I was given a minus sign, so my binomial starts minus, opposite plus, AP always plus. Cube root of each one gives me sine of x, cosine of x. No, this time I kept the x's in there. Go figure. All right, here we go. Sine x times itself, sine squared x. Sine x times cosine x, sine x cosine x. Cosine x times cosine x, cosine squared x. Now, one thing I want to point out, you probably heard this from your algebra teachers, that when you factor this perfect cube, this trinomial here will never, ever, ever factor. But when you're in trigonometry, doesn't mean it's not going to factor, but it may simplify. Sine squared x plus cosine squared x simplifies to a 1. That's not factoring it. That's simplifying it. So this is our final answer. Sine of x minus cosine of x in one binomial, 1 plus sine of x times cosine of x in the other. All right, example 2. Perform each indicated operation and simplify so there are no quotients. Oops. Cotangent theta plus 1 over cotangent theta combined to one term. So to do that, I need to add these two together. So this cotangent theta has to be over a cotangent theta. So I'm going to multiply that top and bottom to get cotangent squared theta plus 1. Oh, wait a minute. That's one of our Pythagorean identities. That's cosecant squared theta. All right, now that we are in one fraction, now it's time to simplify. We don't divide. All right, we're going to multiply by its reciprocal. So my cosecant squared theta, 1 over sine squared theta. Cotangent theta is cosine theta over sine theta, but I had to flip it when I multiplied by its reciprocal to get sine theta over cosine theta. One of the sine thetas will cancel, and that will give me 1 over sine theta, which is cosecant theta. 1 over cosine theta is secant theta. Now, don't get me wrong. You could have gone up here to the top and changed this to sines and cosines and this to sines and cosines. Flipped it, and then the only downside is both denominators would have been different. You'd have to be multiplying sines and cosines to the numerators and denominators to get them to be the same, but it would still simplify out to here. Part B. Right away, let's get rid of all this division. So I'm rewriting this as cosine x divided by secant x, sine of x divided by cosecant of x. All right, change them to sines and cosines, so 1 over cosine of x for secant of x, and cosecant of x is 1 over sine of x, multiply by their reciprocals, we get cosine x times cosine x. That'll be cosine squared of x. Well, wait a minute. That'll be sine squared too. And that adds up to be a 1. Part C. Okay, here we're going to have to put parentheses around our denominators. They're not like denominators because one's a plus, one is a minus, but it is a conjugate pair. That's that difference of squares that we saw earlier when we were factoring. We need to multiply. So this left side gets multiplied by 1 minus cosine of x top and bottom. This one gets multiplied by 1 plus cosine of x top and bottom. That way I'll have common denominators. 1 minus cosine of x times 1 plus cosine of x. Now, on the top, 1 minus cosine x gets multiplied by 1. No change to that binomial. However, over here, don't forget to grab the minus sign. Distributing the negative 1 will change that 1 to a minus and that cosine x to a minus. 1 minus 1, that's going to cancel. Negative cosine of x times negative cosine of x is going to be negative 2 cosine of x. You FOIL out the bottom. Remember, that will give you a difference of perfect squares. So just take the 1 and square it, minus square the cosine of x. Oh wait, that's going to be sine squared of x. That's part of my Pythagorean identities, manipulated, if you will. And now we're going to break down the top to a negative 2 times the cosine of x times a 1. So this 1 over sine of x, that will be cosecant of x. Cosine of x over sine of x will be cotangent of x, and the negative 2 will just factor that out and move it out front. All right. Now, verifying identities. You will be given a statement of equality and be asked to prove that it is true. Therefore, you cannot use properties of equality in a verifying problem. In other words, you cannot add or subtract, multiply or divide anything to both sides of the equation as you would when you are solving. That's a different situation. When you're solving for an x or for a variable, you can add and subtract, multiply and divide those same values to both sides of the equal sign. But when you're verifying, you cannot. To avoid this temptation, use algebraic properties of equations that will work with one side and rewrite it to match the other side. So you want to use your fundamental identities. Whenever you see either side of the fundamental identity, the other side should come to mind. Also be aware of equivalent forms of fundamental identities. Try to rewrite the more complicated side. That's the one with more trig functions in it. Let's manipulate that side to make it identical to the simpler side. It's sometimes helpful to express all trig functions in the equation in terms of, you've seen me do it already, sines and cosines, and then simplify the result. Usually any factoring or indicated algebra operation should be performed. So for example, the expression sine squared x plus 2 sine of x plus 1, you might want to factor that as sine of x plus 1, that binomial squared, so you can do some canceling. As you select substitutions, keep in mind the side you are changing because it represents your goal. An expression contains 1 plus sine of x, manipulating both numerator and denominator by 1 minus sine of x would give you 1 minus sine squared x, which could be replaced with a cosine squared x. So these, again, these are your conjugate pairs. Similar procedures for 1 plus cosine of x, think 1 minus cosine of x. Secant of x plus 1, secant of x minus 1. Cosecant of x plus 1, cosecant of x minus 1. Just look at your Pythagorean identities, subtract to one side over to the other to build a difference of perfect squares, and that's what you're looking for. Remember, the procedure for verifying identities is not the same as that for solving equations. Techniques used in solving equations such as adding the same terms to each side and multiplying each side by the same term should not be used when working with identities. All right, so here we go. Verify the following equation is an identity. Cotangent theta plus 1 equals cosecant theta times the binomial cosine theta plus sine theta. And I hope you all agree with me that the right side is much, much worse than the left side. So we're going to manipulate this side. All right, so technically the left side has two terms in it. The right side is officially one term. I need to really distribute that cosecant theta to both those terms to create two terms. So let's get that done. Okay, now here's my goal. Got to kind of think about where we're heading. Once we do this multiplication, now we probably want to go to sines and cosines, and we want to see these answers appear. So cosecant theta is 1 over sine theta. 1 over, hey, perfect. Look at over here on the right. 1 over sine theta times sine theta. That's going to cancel out. That's going to give me this 1. Then hopefully here, cosine theta over sine theta. Yep, that's going to give me cotangent theta. There's my match. I have exactly what I was set out to get. I am done. I verified everything. Very important. Do not skimp on your work here. The more you show, the better. It's like writing your English essay papers. More detail will get you more points. B, obviously, we don't want to start with 1 and manipulate that. We're going to start with the left. So what I'm going to do here is I'm going to separate this. I'm going to call cosine theta as cosine theta times a 1. So cosine theta over sine theta, that will simplify to cotangent theta. And I have the reciprocal of cotangent theta already, 1 over cotangent theta, so cotangents cancel, leaves me a 1. Part C. Let's see, left side looks messier, so let's go to the left. Right off the bat, I see a Pythagorean identity right here. 1 plus cotangent squared theta, I believe, is cosecant squared theta. So what that does is that takes this potential, didn't want to distribute property here, because that would give me 2 terms when I'm all done, and 1 fraction is considered 1 term. So this is a better approach. Now is a time to change this to sines and cosines. And again, we're looking to build a Pythagorean identity on the bottom. So sine squared theta over cosine squared theta times 1 over sine squared theta. Well, what I see is my sine squareds cancel. Oh, that leaves me the 1 in the numerator. That's a good thing. Now I have cosine squared theta in the denominator, but wait a minute. I can write the alternative form of the Pythagorean identity as 1 minus sine squared theta. That's where I want to head to. So now it's a match. Part D, it's really not going to matter which side you manipulate. They're both identical. So I'm going to approach it this way. I'm going to change the left side to make it look like the right side. So again, I have a 1 minus sine theta. What I need to think about is multiplying again by its conjugate. 1 plus sine theta multiplied to the top and bottom. Now watch what happens here. I need a 1 plus sine theta in the numerator. Okay, there it is. Now what do I need to do is I got to somehow get this cosine theta to cancel with something on the bottom. So we're going to multiply this out, and that's going to become a difference of perfect squares as 1 minus sine squared. Wait a minute. 1 minus sine squared theta, we just had that over here. That's cosine squared theta. So we'll substitute that in, and oh my gosh, we said we wanted to cancel this cosine theta on the top. There it is. Let's cancel this cosine theta with one of these cosines on the bottom. Oh, wait. That gives me an extra cosine theta in the denominator. We have a match. So that's kind of how you look at moving forward. This is what I want to get to. Was it a good decision to multiply 1 plus sine theta top and bottom? Absolutely. We'll get that up there in the top right away. Now, if you'd chosen to work with the right side, then you'd have to multiply top and bottom by 1 minus cosine theta, 1 minus sine theta. And again, there's your 1 minus sine theta. Matches, you'd have to get this cosine to cancel with a cosine on the top, and you'd get a cosine squared up there. So either one would be the exact same amount of work. E, we have secant theta plus tangent theta over secant theta minus tangent theta is equal to 1 plus 2 sine theta plus sine squared theta over cosine squared theta. Even though the right side has more stuff, I'm going to go with the left side for the following reason. This is already in sines and cosines. So I think this is what we're going to manipulate first, and I think we should go right away and cancel. Well, wait a minute. I was thinking about going sines and cosines, but I just noticed something here. This is a conjugate pair. So let's do the same thing we did over here. Let's multiply top and bottom by the conjugate pair of the bottom. So I want to multiply secant theta plus tangent theta both to top and bottom. All right, let's see where that takes us. Well, these two binomials on the top, that's just going to be secant theta plus tangent theta, that binomial squared. This will multiply out and give me a secant theta minus a tangent squared theta. All right, now, where can we go from here? Wait a minute. Secant squared theta, tangent squared theta, that's a Pythagorean identity. Let's see, there's my identity for, yep. Okay, wait a minute, secant squared x minus tangent squared x. If I just subtract the tangent squared over from the 1, I can get, what? I can replace this whole denominator with a 1? Well, I'm in business there. Oh, wait a minute, though. Okay. Oh, no, we're still good. I was worried because we lost how we're going to get a cosine squared theta. But I forgot. We got to turn these into sines and cosines. So I'm going to FOIL this out. Secant theta times itself is secant squared theta. Secant theta times a tangent theta, then the tangent theta times a secant theta gives me 2 of those. And then tangent theta times tangent squared is going to, tangent theta times tangent theta will give me a tangent squared theta. I kind of got tongue twisted there. Okay, now is a good time to convert these all to sines and cosines. So we're looking at 1 over cosine squared theta, 2 times 1 over cosine theta times sine over cosine for my thetas, and oh, wait a minute, sine squared theta over cosine. Hey, check out my denominators. We need to have cosine squared there. Okay, cosine squared. Multiply these together. Cosine squared, cosine squared. You don't suppose there's my 1 plus 2 times the sine theta plus my sine squared. I have everything in place. There it is. Now, again, you could have changed these all to sines and cosines first, but you would have been doing an awful lot of writing out right off the bat. So sometimes it's good to change the sines and cosines, sometimes it's not. You would have had all kinds of fractions inside of fractions here. So we've matched what we were looking for. And that's our 3-2.